Let's go ahead and get started. So today we are happy to welcome Thomas Baumgarte, who comes to us from Bowdoin College in Maine. And Thomas is one of the world's experts on numerical relativity. Is
that me?
Sounds right. Let's get the sound working regularly. I'll continue with the introduction and we can get that fixed in the following. So, in addition to the history that Steve provided, that he got some degrees in Germany, but spent a lot of time doing his dissertation at Cornell, he is also known for his two textbooks on treatises on numerical difficulty. The first being a classic text, and the second one being within the last couple of years on starting numerical relativity from scratch. So if you are interested in learning about that, and today he's going to tell us specifically about the capture of primordial black holes. So let's go ahead and welcome Thomas.
Thank you. Thank you. Thank you very much, and thank you for inviting me and for your introduction. Please, if you cannot hear me, let me know in some way or other. Okay. As you said, my home institution is in it's Bowdoin College. That's in Maine, where it is February right now. Okay. But I've been very fortunate to spend the last couple of months of my semester of my sabbatical at the University of Arizona in Tucson, where it's also February. I understand that. But it feels very different, and I can see why people might get used to this. Anyway, it's been a pleasure to be here, and it's a fun opportunity to visit you. I'm very happy to be here. I'll tell you about some primordial black holes today, and basically primordial black holes, just to make sure we're all on the same page. Many of you know a lot of maybe all of this already. Primordial black holes are black holes that may or may not have formed in the early universe. Okay, and I'm not going to try to convince you that they exist or that they don't exist. We don't really know. But they were proposed about 50 years ago by people like Zeldovich and Hawking and Ian Carr and other people. If they do exist, they may actually make up, or maybe all of the dark matter, maybe part of the dark matter. So in the process, they may actually solve one of the big outstanding astrophysical problems of our time. Okay, but we don't really know how they might have been formed. There's questions, but we also don't know that they would not have formed. Okay, so while we don't really know, I think it's fun to think about observational consequences, how we might see them, and what they might do to other stars. And so basically that's what I'll talk about today. Okay? And speaking of fun, let me actually talk about something completely different. Namely, does this work? Well, maybe not. Okay, then we'll do it by hand. The Tunguska event, which you may have heard about. That was all we know. Okay, it was a huge atmospheric explosion that happened in June 1908 in the remote part of Siberia. Again, it was an atmospheric explosion. There are eyewitness reports. There was a lot of damage to trees. I think if I remember the numbers right, about 80 million trees were flattened of an area of 2,000 square kilometers or something like that. So from those numbers, we can estimate what the energy was that was released in this event. There are speculations on what it might have been, maybe a stony asteroid. So afterwards, years later, basically people went there in expeditions to find asteroids or any hint on what might have caused this explosion. But there was never any asteroid found. Okay, there's also no impact crater. At some point, there was a speculation that maybe this lake is the impact crater, but then people said, no, that lake was there before. So it's completely unclear. So to this day, it's a mystery as what created this atmospheric explosion. And now I have to tell you, if I were sitting in the audience, I would get very nervous right now because I think, please don't tell me it was a primordial black hole. Okay, and you can relax. I'm not going to tell you that. I don't need to because other people have already told you that. Okay, namely Jackson and Ryan, actually in 1973. Proposed that it was, in fact, a mini black hole, a primordial black hole that hit. And basically, maybe your reaction is the same that my reaction was when I first heard about this, and this, come on, this is absurd. But then the more you think about it, the less absurd it actually is. So let's go through some numbers. Okay, so first we should ask, okay, if it were such a black hole, how would it actually interact with the Earth? And the answer to that is it would be by dynamical friction. So dynamical friction is this process by which if you have, let's say you have a fluid or gas, you have an object flying through this fluid, then because of the gravitational attraction, gas or fluid particle will converge basically in the wake of this particle as shown in this image. Okay, let me see if I can. There we go. Okay. So basically these particles will converge here. There will be a shock wave in the wake of this object. There will also be, this will create an overdensity behind the particle. And therefore there will be an effective gravitational force slowing down this object. Okay. But because these particles converge, they form a shock. There will also be heat created here. So that creates this interaction between this object and this atmosphere. Okay. Now, this picture is taken from Rudderman and Spiegel, which actually has a very nice derivation of this formula that I'll refer you to, so you can look that up and where this all comes from. But basically, the force, which I call the deflection force, because these particles are being deflected, is something like 4 pi. We know what 4 pi is, right? Then rho is the density of the fluid or the air that this object goes through. Then the gravitational constant, m is the mass of the object, and v is the speed. And then there's this funky Coulomb logarithm, log lambda, which comes from an integration when you figure out from where to where do I need to integrate. It's this distance s, you integrate over the impact parameter, essentially. And really, it's not quite clear where you should start and where you should end. That's the bad news. But the good news is it doesn't matter all that much because it enters only logarithmically. Okay, so typically this number is of order 10. Okay, so what we could now do is say, okay, great. If this is the force, then the energy that is released is the force times the distance. But we know how the distance from eyewitness reports that this object flew through the sky was something like 100 kilometers or something. So we can equate that to the explosion energy, which we also estimated from the damage that was done. And so by inserting all of this, we can actually get a number for the mass. Okay? In this case, the mass is something like 10 to the minus 11 solar masses. Okay. Now, that is actually an interesting number because if you look at recent constraints of what primordial black holes and what masses they might be allowed, 10 to the minus 11 is exactly in one of those allowed windows. So this is a figure taken from Carr and Kuhnel, a review of current constraints on primordial black holes. There are lots of different constraints. Here, there's Hawking radiation that would make black holes evaporate. There's microlensing, even cosmic microwave background. So basically lots of constraints, but there's some windows that are called windows of opportunity. The biggest gaping window is between about 10 to the minus 16 and 10 to the minus 10 solar masses, where we don't have any constraints. So in that window, these primordial black holes could actually make up the entire dark matter in the universe, right? And so the number that we're getting here is right in that window. So that's kind of, interesting, okay? Now you could ask, but wait, if a black hole in the Earth, they don't play well together, wouldn't the black hole just suck up the whole Earth? Wouldn't it destroy the Earth? No, it would not, because actually, if you figure out how big is such a black hole, okay, does anybody want to do that in their heads? No, probably not. Okay, so solar mass is about 1 kilometer, right? In gravitational units, 10 to the minus 11. So now we're talking angstroms. So basically, these black holes are atomic size. They're tiny. So they would go right through the Earth, okay? So basically, it's 100 angstrom or so. It would go right through the Earth. And so, no, it wouldn't do a lot of damage, okay? The Earth would definitely survive, okay? So that is that. Now, the next question you could ask, but come on, what are the chances? How many of those are there? How often would that happen? We can estimate that too. We could go to the literature, look up the density of dark matter in the solar neighborhood. Okay, it's something like that, okay? And then the event rate is just given by the number density times the cross-sectional area. Let's say anything between here and the sun, okay, just to get some estimate for how often would something like this fly through the solar system, and times the speed. I inserted the speed for the local speed of the galaxy, rotational speed. Okay, and if you insert numbers, you get this scaling. Okay, and it's 10 to the minus 8 to 1 over second. Remember, there's 10 to the 7 seconds in a year. So this is on the order. You get basically about once a decade or every few years, one of these mini black holes actually would fly through the solar system. And there are actually people who are now using positional data, precession data to the moon, for example, to figure out whether in our historical data for these distances, we have any evidence of the primordial black hole flying through. Okay, so actually, you know, I mean, I inserted very optimistic and large numbers here, but nevertheless, it's not absurd that a primordial black hole might hit the Earth. Okay, sure, please. So, excellent question. Okay. So basically, it's difficult to, I mean, it might have created a crater. It's a very swampy area. It's very difficult. And also the other thing is, it's historically actually quite interesting. It was in 1908. I think the first expedition to go there was not until actually after the revolution. And so it took a long time, and things have grown. So it's messy. Okay. And I don't know. There are lots of articles to this day written about it. It's very weird. But let me ask another question. So you're saying, why isn't there not a crater coming in? Okay, and I told you this thing would fly right through the Earth. What will happen on the other side? Guess what? So basically, what I find is really neat about this idea, these authors in the last paragraph of the paper say, we could check this. Because if the black hole went in one way, it comes out the other way. Think exit wound, right? So there should have been a similar explosion on the other side of the Earth. So we could actually go back, look at atmospheric data, seismic data, and see whether that happened. And in fact, a year later, there was another paper in Nature, okay, by Beasley and Tinsley, who did exactly that. They looked at those data, and their data, you can, for example, the original event, you can definitely see in this atmospheric data, okay? But there was no hint of the exit wound, and therefore we know that this didn't happen, okay? Maybe, right, but then you would have to explain why it would do that, okay? This dynamic friction is not strong enough to do that, okay? Your real question should be, why the heck did I just waste 10 minutes or something telling you about something that didn't happen? Okay, yes, but yeah. 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 It would, absolutely. But basically, that would now be in the interior of the Earth, and there should definitely be earthquakes. Therefore, you look at seismic data, it absolutely would. Not only, yes, no, you're absolutely right, of course, yeah. Okay. Yes, so I think they primarily looked at atmospheric data, but I think they also looked at seismic data, and there's no evidence of the exit wounds, right? So, yeah. So again, why did I tell you about this? Okay, frankly, it was fun. Okay, that was one reason. Okay, but the other reason is actually it already allowed me to introduce three key things that are important for the rest of the talk. One is the whole thing about dynamic friction, so that'll come back up. I also told about mass windows, so I showed you this plot. Okay, so I'll be talking about primordial black holes in this mass range, and maybe this B around 10 to the minus 6 solar masses, okay? And also, maybe we believe that actually collisions with stars will happen, and that should raise the question, well, what does actually happen when that happens? Okay, so how can primordial black holes be captured by stars? Okay, and basically they will if enough energy is captured. That comes back to your question. Okay, basically, in order for the black hole to get stuck in an object, you need to dissipate enough energy. Okay, for what stars is that possible? Okay, so here's basically an outline, if you want. So questions that we could ask about this capture of primordial black holes is like, what kind of stars can capture primordial black holes? Okay, how long will this process take? How sensitive is the process to details in the physics? How and when does this primordial black hole actually trigger the star to collapse? Okay, might this scenario be a promising source of gravitational radiation or multi-messenger astronomy? Okay, this is kind of a cartoon what this might look like. So here's the star. This color shading kind of symbolizes the density. Here's an orbit where a black hole comes in. It loses some energy, enough energy to be gravitational bound afterwards. Then it comes back out, goes through it many times until it finally sinks into the star. And then in the next plot, I'll show you the last few orbits until finally, basically now that inside the black hole will also accrete mass. At some point, it will have accreted so much mass that the whole star collapses dynamically. This is kind of what the orbit looks like. This is for an orbit that I started artificially with a very large black hole mass. Because for the tiny black hole mass that we talked about before, you have many, many orbits before this happens, we wouldn't see anything on this plot, okay? It looks like you have a question, but no? No, I'm sorry, no. So, so basically, they will always accrete mass once the inside, if this black hole is inside the star, it will accrete mass, okay? And so that means the black hole will grow. But initially, we'll see this later, we'll come back to this, okay? Initially, it grows very slowly. It's only in the end that it grows very rapidly, right? Okay, so a couple more things. Many of these estimates that I'll tell you about in a minute have already been considered by a lot of a number of different authors. So I want to just recognize that. Also, a lot of the stuff that I'll tell you about is preliminary. Okay, so this is still a construction zone. Okay, we're still working on this, but there's already some fun stuff to tell you about. Let's start with some estimates. Okay, so let's assume that when our star and the black hole are far apart, okay, they have a relative speed that is small compared to the escape speed of the star, okay? So that's, in typical scenarios, that's a very good approximation, okay? In that case, once the black hole hits the star with the surface, it will reach a star approximately with the escape speed. It will, okay? Okay, and you're still looking troubled. That makes me nervous. Okay, no, you okay. All right. So that will the speed. So this black hole hits this star roughly with the escape speed. Now, how long will it take for the black hole to go through the star? Well, something like the distance over the speed. And if you insert numbers, you get something up to factors of unity, right? R cubed divided by m. Okay, and that you recognize as the dynamical time of the star. So that speed, the time that it takes for the black hole to go through the star on the first passage is roughly the dynamical time scale. Okay, so for a neutron star, for example, that will be a millisecond, give or take. Okay, all right. How much energy is dissipated in this first passage? Well, the energy we've already said is the force times the distance. So I'm being kind of sloppy on whether I keep factors of 2 or not, okay? But it's kind of the force times the distance. This is dynamic friction, which we've already seen. This is R. And if I now replace rho with the average density, so that would be m divided by R cubed. And if I replace V0 with this m divided by R term there, then I can express this in this way, okay? So just some algebra, all right? So let me repeat that. This was the energy that is dissipated in the first time. For the black hole to be captured, this energy that is dissipated must be greater than the energy that we started out with, so that afterwards we have a negative energy so that the black hole is bound, okay? So that means this energy must be greater than the kinetic energy that they had at the beginning, which is 1/2 mv infinity squared. And that means I can now, I can solve for the mass ratio m divided by big M, and I see that for the black hole to be bound after the first passage, we must satisfy this inequality. This will be a good time to tell you what my symbols mean, okay? So by little m, I mean the mass of the black hole, the little guy, kind of intuitively. Big M is the mass of the star, the big guy, okay? And so we're looking at this ratio. And again, log lambda is order of magnitude 10. Now, what that means is if we want to capture a small black hole, we want this ratio to be as small as possible. That means we want the escape speed to be as large as possible. So now we can scratch our head and ask, what stars do have the greatest escape speeds? And that's neutron stars, okay? And if you can insert numbers, you get about some 10 to the 5 kilometers per second, order of magnitude, okay? So neutron stars are our best candidates for capturing primordial black holes. But even for those, if you insert those numbers and if you make some assumptions about V infinity, you realize that even they can barely capture these black holes in the upper range of this mass window A, okay? From 10 to the minus 10 solar masses, maybe down to 10 to the minus 12 or something. Those black holes you can capture, all right? You ask about accretion. Okay, so we can now estimate the rate at which the black hole will grow. That is, we can estimate from the Bondi accretion rate, okay? And which tells us that the rate at which the black hole will grow will be 4 pi's, and then there's an eigenvalue lambda that I'll come back to later. It's a non-dimensional number, typically of order unity. Then there's the density, m is the black hole mass, and a is the sound speed. Okay, so this is what Baumgarte told us about in 1952. Okay, and you notice that as long as little m is small, this accretion rate will be very small. But when m increases, it will actually start growing faster than exponentially. We'll see that in a minute. Now we can define an accretion timescale, the timescale for which the typical timescale for the black hole to grow. That is m divided by m dot. If I insert numbers in here and again replace rows and a's with m's and r's, I get something like big M divided by little m times the dynamical timescale. Okay, so basically, again, if we have a big mass ratio, this could be as much as 10 to the 10 dynamical timescales. That's a big number. Okay? Now, there's one more timescale that we should talk about, and that's the capture timescale. So first, we can estimate the number of passages that we need for the star to be swallowed. And that we can estimate from this. Basically, n is the number of passages. Let's say in each passage we lose an energy delta E, then this must be equal to the binding energy that we end up with which is of this order. And now I can basically delta E, we estimated before, we can rewrite that in some way, and by then solving for n, I get this number. Okay, so the total time then that I need for this capture is the number of orbits times the orbital time scale, but that's now like almost a Kepler orbit, so that's much longer than the transition time scale. So this is much greater than the transition time scale, which was of order m divided by little m times the dynamical time scale. And that was similar to the accretion time scale. The bottom line of this is this. There's a hierarchy of time scales. Each one is, the ratio is, each one is the mass ratio. Think 10 to the 10 or 10 to the 6 or something. The biggest one is the capture time, then the accretion time scale, which is, again, much greater than the transition timescale, which is similar to the dynamic timescale. And finally, there's the timescale of the black hole, which is, again, much smaller. So there's a vast range of timescales. And what that tells you is there's no single technique that can use to simulate each one of these aspects. And instead, we need different techniques to analyze different aspects of this problem. Okay, and that's exactly what the rest of the talk is going to be about. Here's an overview of my talk, okay? 3 parts. The first part, good news. We're already done with this. We went through some crude estimates, okay? Now I'll tell you about some point mass approximations that we can use as long as the black hole is small and as long as we can neglect any feedback of the black hole on the star. And then in the last part, I'll tell you about some dynamical evolution, so true numerical relativity simulations, where we actually treat the black hole and the star self-consistently, and we can actually study the feedback of the black hole on the star. We can check how does a star react to a black hole going through it. Okay, so let me start with these point mass approximations. Now, if we did this in Newtonian physics, then this is what we would do. We would write down Newton's second law, ma equals the effective mass, okay, the effective force, okay, the total force. And in this case, there are 4 components to that. There's the gravitational force exerted in the black hole by the star. There's the deflection force that we already talked about. There's another force, is the accretion force, because actually the mass of the black hole changes. So that acts like, it results in a term that acts like a force. And finally, the black hole will emit gravitation radiation. So there's a radiation reaction force that takes into account the losses of energy and angular momentum through gravitation radiation. This is what we would do in Newtonian physics, but I will not do this in Newtonian physics. Instead, I'll solve this in general relativity. If it were not for these last 3 forces, if it were only the gravitational force, then we would solve the geodesic equation, as some of you may know, okay? And what we'll do then is we'll solve the geodesic equation, which takes into account the gravitational force itself, and we'll add to that these other forces as small deviations. So basically, this is what it'll look like, okay? So if you're not used to these indices, don't worry about it. This is the acceleration. I divide it by m. There's one term that basically plays the role of these terms, and then we have these other forces that act as deviations. And in the next few slides, I'll just go through each of these terms and explain just in a few words, give you a little bit more detail what we do. As for the stellar model, we solve the Oppenheimer-Volkoff or Thommen-Oppenheimer-Volkoff equations to construct an equilibrium model of star for a given equation of state. For almost everything I'll tell you about today, I'll use a polytrope with a polytropic equation of state with gamma equals 2. In a couple of places, I will have a different gamma, but I'll tell you. And then we solve these relativistic equations of hydrostatic equilibrium. That gives you an equilibrium model. It gives you a relativistic model of these stars. And they give you the background metric and these Christoffel symbols, gamma, A, B, C, that entered into the geodesic equation that I showed you on the previous slide. Okay, so that's how they're taken care of. Dynamic of friction, I already told you about. When I told you about it earlier, I gave it to you in this form where I said this function I is just a log lambda. Okay, for the aficionados, we can do a little bit better. We can actually follow, for example, Yves Ostreicher and Barros in basically writing a better approximation for this function I, which takes into account the forces close to, for a subsonic motion and close to the Mach number equals 1. So again, it doesn't really matter. It's a detail, but we use a better approximation for this I. So only for this part, it's a fixed background. So we solve these static hydrostatic equations, and then we have a fixed start, and we ignore the feedback of the black hole disk. We'll get back to doing that self-consistently in a minute. Okay. I wanted to spend a little bit more time talking about the accretion again. Okay? So I told you before, so this accretion force that results from the fact that the mass of the black hole is not constant and it grows. Okay? And it grows at a rate that if it's static, if it weren't moving, at a rate that is given by this Bondi expression. Okay? And now if you look into textbooks, then you could look up what these lambdas are. I told you before that these lambdas are, sometimes they're called accretion eigenvalues, okay? And if you look into textbooks, for example, Shapiro, Tucholsky or so, they will tell you that these lambdas are given by these numbers where gamma is the polytropic index. So you could, for example, for gamma equals 4/3 or something, you could look up what it is, happens to be 1 over square root of 2. It is just numbers, okay? These are true. This is what you get in the Newtonian limit. But if you think about this long enough, you realize that, but wait, okay, what happens if I insert gamma greater than 5/3? Okay, because when gamma, this works, this is true for all gammas up to 5/3. Okay, so what happens if gamma is greater than 5/3? Usually that's not particularly relevant, except for in neutron stars where you have stiff equations of state. So for neutron stars, you need to know what is this lambda for gamma equals 5/3. How do you do that? Well, in that case, you have to solve this relativistically. You cannot use a Newtonian approximation. And something really neat happens in that case. Okay, so this is the question, what happens there? Okay, and so basically, again, here's this expression. Here's a puzzle, okay? Let's say I took this, let's say I assume that lambda is just a number of order unity, and I evaluated this for gamma equals 2. Well, for gamma equals 2, it turns out that the density rho is proportional to the square of the sound speed. So replace rho with a squared, then this whole thing goes with 1 over a. Now take the limit of low densities, hence low sound speeds, and this number, you get an accretion rate that goes to infinity. That clearly makes no sense whatsoever, okay? So what happens? Well, actually, this relativistic treatment comes to the rescue because it tells you that for gamma greater than 5/3, lambda no longer goes to a non-zero constant and actually goes to 0. So for example, for gamma equals 2, if lambda happens to go to this number, okay, and now we have an extra a upstairs, so now we have 3 factors of a upstairs, 1 from lambda, 2 from rho, they cancel, and in fact, the accretion rate goes to a certain fixed number. So now it's finite, that's good, but it's still a very confusing result because what this tells you is that for stiff equations of state, steady state accretion onto a black hole will take a minimum value. There is a minimum value below which you cannot have steady state spherically symmetric adiabatic accretion. Very confusing, okay? But there it is, okay? And actually, this is work with one of my undergrads, Chloe Richards, who is now a graduate student at the University of Illinois. She did beautiful work on this. Finally, there's this radiation reaction force, which we just look up at Peters and Matthews. Oh, this is all very well established. So there you go. And now we can do various different calculations. Everything that I'll show you, I'll assume V infinity is 1 km/s, which is really on the lower end. Okay, but that might be maybe in the distribution. It's not totally unrealistic. And for the neutron star, I assume I'll scale everything to a star There's 1.4 solar masses, which is a typical mass for a neutron star, and a radius of about 12 kilometers, which is consistent with nicer results in other observations. Okay? And then we can do all kinds of calculations. We can, for example, compute, well, how many orbits will it take for the black hole to be captured? We can do this for different masses. So here, mass ratios between the initial black hole mass and the stellar mass. And guess what? Basically, they scale exactly as we had predicted before. That's kind of nice, also not particularly exciting, but there you go. Okay, we can also compute times. These hinge very much on how much time you spend in the first orbit, so they depend very strongly on V infinity. But nevertheless, so you notice these are times that span from, just a few seconds or so to years, but they're all shorter than the Hubble timescale. So this would actually happen in the age of the universe. What's more interesting is what happens once this black hole is swallowed. Okay. Now, this is a point where I'm very nervous because this is supposed to be a movie, so we'll find out now whether this works or not. And it does. Oh, look at that. Okay. So here's an orbit. Okay. So this is after the black hole is captured. It now zips through the star. Very appropriately, I colored the black hole black. How else would you do that? Okay. You notice how this orbit is eccentric. It rotates. It becomes smaller. The black hole sinks to the center, and it's only that was pretty neat, right? So anyway, so basically, should we do that again because it's so much fun? So here's this black hole. It zips through the star. You notice how the orbit rotates. And while it does that, the polarization of the gravitation wave also changes. The point is when the black hole orbits along an axis, either like this or like that, the gravitation wave signal will be dominated by H plus. On the other hand, if the black hole orbits along the diagonals, it will be dominated by H cross, just the polarizations, okay? So it sweeps through these different polarizations, okay? Now, truth in advertising, this plot I had to make with an artificially large black hole. I started with 10 to the minus 4, so that's large. And I also artificially sped up these frictional forces, because otherwise we would be sitting here for a long time watching this movie, and I didn't want to do that to you, okay? So more realistically, so here's some snapshots. This is for 10 to the minus 6 solar masses, and there's some snapshots. Here's after the black hole is first captured, then a little while later, and in the end, it sits right there at the center. This is the emitted gravitational wave signal. And you notice how, oops, that's not what I meant to do. Okay. No, there we go. Okay, you notice how the gravitational wave signal becomes weaker as the black hole sinks to the center, but the frequency actually does not change much, okay? This is for an almost grazing capture, where the black hole enters basically the star at a very shallow angle. We can also look at an almost head-on capture, where we have an orbit similar to what I showed you in the movie. And again, basically this orbit will rotate, it will turn, and there are different snapshots, and then we get a similar qualitative picture that basically the orbit. Okay, so one thing that we observe is the orbit does not circularize. So these forces are not effective in circularizing the orbit or reducing the eccentricity. The frequency, the orbital frequency, remains nearly constant. And that makes sense because from Kepler's law, omega, actually, you know what, this should be omega squared. I'm sorry, this is squared missing, right? Omega squared should go with m divided by r cubed, but m is the enclosed mass. So if we approximated the star as having a constant density, m would be rho r cubed up to factors. Then we're dividing by r cubed, and it's just rho. So basically the frequency will remain roughly constant. The amplitude, on the other hand, goes with the second time derivative of the quadrupole moment I, which is roughly mr double dot. Now we can use the equation of motion to replace r double dot. That gives us the big M divided by r squared. And basically then we can again replace m with rho r cubed. 2 r's cancel, and we end up with an r. So notice the characteristic of this gravitational wave signal is very different from an in-spiral. The typical binary in-spiral, we talk about a chirp signal. You've probably seen this from LIGO observations. Why is it a chirp signal? We call it that because both the frequency and the amplitude increase with time. This has a very different characteristic. The frequency will remain constant, more or less, and the amplitude will decrease. So this will be very easy to distinguish. as a gravitation wave signal from an inspired signal. It's a completely different signature, all right? Also, we notice that the orbit precesses. And you know what? That, I think, is really neat. And therefore, I would like to explain that. This is a really neat little detour into classical mechanics. So let's have some fun with classical mechanics for a few minutes. Let's talk about orbits. Let's pretend we just have a simple central force. If we have a central force, then the potential is a function of r only. And a typical orbit might look like this. You get all these pretty Rosetta figures, right? And you stare at this and you realize, I now ask you, what is the period of this orbit? You realize there's two different ways of defining that. I could define the period by saying I go from the largest distance away once around until I'm again the largest distance away. That will be from aphelion to aphelion. Actually, usually we talk about perihelion to perihelion, but it's messy down here. It was too messy to draw. That's why I drew it that way, okay? The other way of drawing it would be, then how long would it take for this orbit to go around exactly once, i.e. complete to an angle of 2 pi, so an advance of the angle 2 pi. That would be like this, okay? And if these two times are not the same, then you get a so-called peri-astron advance. That means that the orbit will rotate, okay? Now, sometimes we also look at that as an effective potential, okay? So I'm sure you've seen this from many introductory physics classes, okay? And in fact, maybe you've taught it in many introductory classes. Okay? And basically, the first thing we always point out is that there's the circular orbit. For the circular orbit, we are at a minimum. Okay, at a minimum, the derivative of the effective potential is 0. If the derivative of this effective potential is 0, then that means that V prime is related to the angular momentum L. L is related to the speed, how fast this thing advances in phi. And so with some hand waving, maybe you will believe me that tau phi is related to V prime. Okay. Should I wave my hands a little bit more? Are we good? Okay, good. Right. How about nearly circular orbits? For nearly circular orbits, we draw an energy diagram. We say, okay, there's basic constant energy. So now basically these two turning points, and this particle goes back and forth between these two turning points. And of course, the time tau r corresponds to the time that it takes to go from this point to the other turning point and back, okay? Now, if we're really very close to the minimum, then we can replace this potential with a parabola, okay? Because that's the leading order term. And now we can do the same exercise for this parabola. How do we draw the parabola? We have to match the second derivative at the minimum to the real effective potential, okay? Now, once we have a parabola, this is another well-known problem. It's the harmonic oscillator. We haven't talked about harmonic oscillator in a long time, right? So it's about time it comes up. For the harmonic oscillator, we know exactly what the time is to complete a period. And now you realize that this time must be related to the second derivative of this because that's how we built this parabola. Long story short, there's a neat way to compute the ratio between these two times just from the first and the second derivatives of this potential, okay? And whenever the ratio is different from 1, okay, or an integer number, then we get a peri-Astron advance. Let's talk about a couple of examples. One is our old point mass potential, in which case V equals r to the minus 1. We could insert that into the expression. Upstairs, you get a minus 1, there you get a minus 3, and a plus 2. So guess what? It's minus 1 divided by minus 1. So we get exactly 1. So the same. That's our Kepler orbit, okay? And the Kepler orbit, that's infinite, okay? So we have exactly 1 peri-Astron per orbit. It's right there. The closest point is right there. There's 1 per orbit, okay? Now notice when our black hole first approaches the star, then to good approximation, this is the orbit that we have, okay? Here's another example. The harmonic oscillator, okay? So now V is proportional to R squared. Now you can insert this. I'll let you do that as homework exercise, but you will find that tau r is tau phi divided by 2. Now we have orbits like this, where there are 2 peri-Astrons per orbit, 1 on each side, okay? And in a minute, I'll argue that in fact, these orbits correspond to the endpoint of this capture, okay? But before I do that, I'll remind you of a really neat theorem that you may have learned about in classical mechanics or that you may have taught in classical mechanics. And that's Bertrand's theorem, which tells you that there's only 2 potentials for which all orbits are closed. And those are precisely the 2 that we just talked about, n equals minus 1 and n equals 2. Okay, so it's kind of neat that in this capture of this primordial black hole, you go from one example of Bertrand's orbits to the other one. Okay, all right. Now, why is it that in the interior, we get this second case, the harmonic oscillator. Well, if we're deep inside the star, let me approximate rho by the central density rho, pretend it's constant. Then the mass is just the integral over that. So I'll get something like rho c times r cubed. From the mass, I can compute the potential, and you get this well-known result that the potential is just a parabola, right? That this is the parabola. And now you realize that's exactly what we just saw. It's basically the potential is proportional to r squared. In that case, tau r divided by tau phi is 2. Okay, so we get closed orbits. It's an integer. Okay? And that means the periastron advance is 0 for closed orbits. When you get closed orbits. Okay, constant density star. Now you should say, but wait, the star is not constant density. Really, you have, So you said, okay, how do we handle that? Why don't we start with a Taylor expansion? So I'll add another term there. The density is an even function of R. So the next term that enters in the Taylor expansion is the rho double prime times R squared. Now this new term will give rise to a new term in the mass, which goes with R to the 5th. Now that term gives rise to a new term in the potential, which goes with R to the 4th. Okay, now we can again evaluate our expression for the ratio of these timescales. And now you find from that that the periastron advance is this. Okay, so it's now non-zero. The departure from constant density at the center leads to a periastron advance. Okay, now what is neat about this is the following. This rho double prime divided by rho, that may be different for different stars. In fact, it depends strongly on the equation of state. Okay, so what does this periastron advance do? It makes the orbit rotate, but we've also seen that that leads to a change in the gravitation wave signal. So if we observe this, then if we could observe this signal, and if we could see the beats in the gravitation wave signal, that would give us a constraint on the equation of state. And to demonstrate that to you, here's another little movie. So there's 3 different stars. They all have the same mass. They have the same radius. They're identical, except for the equation of state. There's an extreme case, gamma equals infinity. That's a constant density star. Then there's gamma equals 3, which is kind of a stiff equation model for a neutron star. And gamma equals 2. They're the black holes. And if I let this go, then you will notice that basically the softer the equation of state is, the more rapidly orbit will turn, the more rapidly the gravitation wave signal will change from being dominated by H plus versus H cross. And that means you have shorter beat periods in there, higher beat frequencies for softer equation of state. So basically these are scaled for a black hole that is 10 to the minus 6 solar masses roughly. Okay, for a star that is at a distance of about 10 kiloparsecs, so somewhere in our galaxy, and that gives you a gravitation wave signal in the order of 10 to the minus 24, which is safely outside of what LIGO can detect, but that is observable by the next generational detectors. So basically, if a neutron star in our galaxy caught a black hole of this mass, we would be in business, we might be able to observe these beat frequencies, and they would give us a very strong constraint on the equation of state, which I think is just such a neat application of classical mechanics here. Now, the skeptics among you should object, because didn't I just tell you that for a constant density star, there's no periastron advance? So why is this advancing? It is because while I told you the truth, I did not tell you the whole truth. I did not tell you that actually these are relativistic simulations. And there's a relativistic effect, which is actually stronger than Newtonian effect, but it has the same dependence on the equation of state. And this relativistic effect gives you a periastron advance even for this constant density star. All right, okay, yes. So here, just some takeaways from these point mass simulations. Okay, after capture, we've seen that this primary black hole sinks to the center. As it does, the eccentricity does not decrease, certainly not significantly. We've talked about the gravitation wave characteristics. So they're very different from an in-spiral. Okay, so basically you have a qualitatively different signal. We've talked about this periastron advance that leads to these gravitation wave beats. Okay, and they're very sensitive to the stiffness of the equation of state. And again, basically the signal should be observable with any luck by next generational next generation gravitational wave detectors. Of course, I'm making one more assumption here, and that is that primordial black holes exist, okay? Anyway, here's part 3. So now basically what we've done is you asked me about this, about the background star. So far, I've held the background star fixed. Now we could ask, okay, but at some point, the star will become unstable. How can, or you ask me, okay, if this black hole goes through the Earth. I mean, come on, is the Earth really going to survive? So in order to answer that, we need to do numerical relativity simulations. Maybe you know about numerical relativity already. If not, I do know about some textbooks that you could read. They make nice presents too. Anyway, so the bottom line is really you do this in 2 steps. You first solve the initial data, which means you construct basically fields that satisfy the constraint equation. They give you the gravitational fields and the fluid at one snapshot of time if you want. And then you evolve these forward in time to see how this system evolves. Okay, I'll do that with a particular numerical code. It's based on the so-called BSSN formalism, and I won't explain that in detail either. And it adopts spherical polar coordinates. That's kind of what's a code that I'm kind of proud of. Okay, it's basically uses a grid that kind of looks like this. It's a spherical grid, and there's a neat way of dealing with the coordinate singularities that you get at the center on the axes. The advantage of using such a grid is that it allows you, I can also use a logarithmic radial grid so that I get very high resolution at the center, okay, and coarser resolution elsewhere. And that allows me to resolve even small black holes, even when stuff is around that, okay? All right, this is what the initial data look like. Okay, so basically, how do I do that? I first build a star, again, by solving the TOV equations. Here's the star. But then I superimpose a black hole that is boosted, so it carries a certain momentum. Okay, and then I can use a trick that is called this puncture method to actually solve the constraints, and that gives me valid solutions to the constraint equations of Einstein's equations. And this is what this would look like. So basically, I now have the ability, I can put the black hole anywhere I want on this axis, and I can give it any boost that I want, any momentum, and then I can evolve this. The first thing that we could try is, well, let's put the black hole at the center, okay, and see whether it accretes at the rate that we predicted from Bondi's formula with all this minimum accretion rate. This is a project that I also did with two of my students, Chloe Richards and Sophia Schnau, who's now a graduate student in Amsterdam. And basically, we first did this for polytropes, but then even for piecewise polytropes, so realistic nuclear equations of state. And actually, we found beautiful agreement with the predictions from the Bondi formula that I told you, and including all of the values that were greater than this minimum accretion rate that we had predicted. And notice this is a vast range of masses. So we did these simulations for mass ratios of almost up to 10 to the 10, okay? So the black hole mass is 10 to minus 10 of the black hole mass. Again, this is possible only with these spherically symmetric grids where you can really zoom in on these tiny black holes. Okay, so this is just a confirmation that this Bondi accretion rate is correct as long as we interpret correctly the dot on this M. The dot is the derivative with respect to time, and we have to be careful, like whose time do we actually mean? An observer at infinity or an observer deep in the sides? Anyway, you have to sort that out, but it all works out beautifully. Now we can do the head-on collision. So now I'll put the black hole at the surface of the star, okay, and let it go. Now you should say, but wait. Maybe you buy that with a spherical grid, I can put the black hole at the center of the black hole at the center of the origin in my initial data. But now, when I let it go, will it not move away from the origin? And will I not lose every advantage of these spherical polar coordinates? And you would, unless you use a coordinate system where you actually move the coordinate grid along with the black hole so that the center of the coordinate grid always stays attached to the black hole. You can do that by using a particular so-called shift vector. And here's a demonstration. Basically, I'm starting out with a black hole. This is the so-called lapse function. It measures the strength of the gravitational fields if you want. If you let it go with the usual techniques that you do, so the initial data are the dotted lines, okay? So the black hole sits right there. If you let it go without using this trick, then the black hole will move away from the center, as you can see here. it will quickly lose resolution. See, there's much more resolution right there, but it loses that, and then shortly afterwards, the code crashes. But with this trick, which I call the fixed point trick, I move the coordinate system with the black hole, so the black hole remains at the origin, and I can evolve to very late times without any problems. Okay, so that's the trick that I'll use in the next movies that I'll show you. For example, here, so the black hole starts out at the origin. And when we watch this movie, the origin will actually fall down. So in these coordinates, the neutron star will move up. But I'll always adjust the range of the plot so that the center of mass will stay fixed, okay? But you will notice the origin going down. The black hole sits there. You cannot see it because it's very small. So I blew up this region here, and then I blew that up again. And there you see that's the event horizon of the black hole, okay? So again, that's a very different length scales. So now let's see what happens here. So this is for a particular mass ratio of about 10 to the minus 2. Here the black hole enters the atmosphere. You see basically a shock front emerging as the black hole goes through the envelope of the star. Basically, it falls through the star. It disturbs the star, of course. Okay, this is 10 to the minus 2. So the black hole has a large mass compared to what we realistically expect. But then notice the black hole leaves the star on the other side. It leaves the star behind. The star readjusts, it wobbles a little bit, but it does not collapse, doesn't do anything. So basically, indeed, we have demonstrated that this black hole can fly through this neutron star without making it collapse or become unstable or anything. Okay? And now the black hole happily moves away from this grid, right? It's now somewhere down there. Okay? So now we could ask, okay, so that was for 10 to the minus 2. Okay, so we see that as long as the black hole mass is sufficiently small, indeed, the black hole can go right through the star. And so I noticed we're kind of running out of time, but I'm almost done. Okay, what we could ask is, okay, from what mass ratio would you expect the star to collapse immediately? And the bottom line is, you would expect that when the black hole mass, when the accretion time scale becomes equal to the dynamical time scale. Okay, so when the black hole can eat the stuff in the star as quickly as the star can actually evolve. Okay, we can use estimates very similar to what I had at the beginning of the talk to figure out that will be the case when basically when little m divided by big M is this ratio where gamma is the polytropic constant, lambda is again this accretion eigenvalue, delta is this central condensation, so the ratio between the central and the average density. And this number is typically about 0.1, okay? So a little bit larger. Now let's try this out for basically, this is a little bit smaller than 0.1, but let's try this out. This advances much faster because the black hole is bigger, so the time steps are bigger. And you see that now the black hole actually does not even leave the star on the other side. Instead, the star wobbles around, collapses, and you see that the black hole is formed, and now you have a black hole. The whole thing collapsed. So, okay, in this case, it collapsed immediately. We could do one more thing. We could take an intermediate mass, okay, and see what happens here. Again, the black hole enters. It actually goes through the entire star, okay? We'll see it just barely emerging on the other side. But then the black hole will turn around because it's now bound, okay? It turns around, goes back into the star. We actually see the shock front reversing as it goes back in. We'll see that kind of what you expect, okay? And you see the star wobbling, and ultimately we will see that the entire star basically will collapse. So now the black hole is growing. You already see how the apparent horizon is growing, okay? And now the accretion rate will increase, and this whole thing will collapse and form a black hole. So these are dynamical confirmations of basically our estimates and of the fact that indeed the star will in general remain stable as long as the black hole mass is small enough. Okay, so these are the key takeaways. Actually, I already just said that. Okay, we confirmed the relativistic accretion rate. We confirmed that the black hole can actually pass through the star and it becomes unstable roughly for these mass ratios. Okay, so here's just a quick summary. I kind of speculated what happens if primordial black holes exist and what would happen if those were captured by stars. Okay, we discussed that this is most likely to happen by neutron stars. We see that these will actually remain stable until the black hole mass about 5% of the total mass is stellar mass. Okay, We discussed how the different time scales for this. We see that the black hole settles down to the center. How do we use the eccentricity after it's being captured? And we discussed the gravitation wave signal. Quite excited about this gravitation wave beats that you get to this the periapson advance. There's another component to the gravitation wave signal when the neutron star finally collapses to the black hole. How strong that is depends on how aspherical it is. Okay. In all likelihood, it will be quite spherical because for small black hole masses, it will have settled all the way to the center. And unless the neutron star is rapidly rotating, it will be quite spherical. So whether or not you get a strong gravitation wave burst from this final collapse depends on the rotation rate on the initial black hole mass. But I'll stop here. I already took more time than I intended to, but it was so much fun. So anyway, thank you very much.